Hi, good afternoon, everyone, or evening, or even for some of you in the world, good morning. And thank you for attending my presentation. You've probably heard a lot already today about, and yesterday, about IoT devices, IoT device management, security, how do you integrate blockchain, integration of machine learning, a whole bunch of different areas of IoT. In this presentation, I'm going to focus on IoT data and IoT data management and how do you handle the large amounts of IoT data. So I'll now switch to the presentation and you'll see me again when we get to the questions. So to start with, IoT is not a silo. It's not something that should be treated separately to everything else. IoT is a part of enterprise data assets. So it needs to be treated as part of a connected ecosystem. And so the IoT data is part of your data assets as an enterprise. It goes with your enterprise data assets, anything you may have in the cloud. And you get best value out of IoT data when it can be integrated with, correlated with, joined with the other data assets that you have. And this is crucial to the digital transformation. If you want to start doing things like predictive maintenance or part management, you start thinking about cybersecurity or predictive monitoring and automated customer engagement and all of these different things, you need to integrate things that you're getting from IoT with data that you may have elsewhere in the enterprise. And this is true across every industry. There are innovations happening across so many different industries with IoT. And it's going to affect everyone at some point. And getting the best value out of IoT really involves dealing with the IoT data. And the challenge today is that there are so many different technologies. You have data that's being generated through websites, applications, like network traffic, devices you may have in the enterprise. And then you have the new wave of IoT devices that are mobile, deliver to cloud automatically. They can be very varied and the data content can be very varied. And so there's so many different technologies you may have already, some legacy data, databases, you may have a data lake, you have messaging systems, ETL and batch systems, and all of these need to work together in order to fulfill business needs, to better serve customers, to deal with orders and inventory and security and real-time reporting. So all of these things need to work together in order to provide seamlessly the best value out of IoT data. The other thing is data volumes. You think about IoT, and there was this study that came out from IDC a few months ago, and they basically stated that today we're generating around 16 zettabytes of data annually. So every year, another 16 zettabytes of data. By 2025, they're estimating that will leap to 160 zettabytes of new data generated every year. And anyone with a math background will recognize that curve. It's an exponential curve. And that means that in every 2 years, we're generating more data than has ever been generated in the whole history of mankind before. And that's a lot of data. Now, of that data, today, around 5% of it is generated and needs to be dealt with in real time, immediately. By 2025, they're estimating that 25% of all data generated will be real-time in nature. So it'll be generated and have to be dealt with in real time. And of that, 95% of it will be generated by IoT. Now, this is the kicker, that you have all of this data being generated, but that thin yellow line is the available storage. So only a small percentage of all the data being generated can ever be stored. There's literally physically not enough hard drives, flash drives, magnetic tape, newfangled crystal structures to store all of the data that's being generated. It's just something that you cannot do. So if you can't store all of the data. In fact, if you can only store a small fraction of it, you're left with the conclusion that you have to process and analyze the data in memory before it ever hits disk, before it ever hits storage, in a streaming fashion. And this kind of streaming approach to things kind of helps you move to a digital transformation where you can integrate and join data in real time, and you can do real-time alerting and monitoring. And you can also use this for integration, so you can combine data together and land it somewhere, whether it's in the cloud or a file system or databases, etc. But really, it's to try and move to a unified technology that incorporates IoT data with the rest of your enterprise data in a scalable fashion, using a inherently streaming in-memory architecture. And it's not just IoT data that is enormous. People don't normally think of things like security data as IoT, but security data can be enormous. If you think about network devices, routers, right? You can have NetFlow data, which generates a lot of data, but if you're doing packet capture on the network, that's immense amounts of data. And so you think about not just IoT, but other sources of data, and that's, you can see where these data volumes are coming from. You have to think about how do you incorporate all of this together and answer important questions. How do you avoid losing or ignoring valuable data while still only storing the minimum? And that kind of gets to the notion of the difference between data and information. Anyone with an information science background will know there's a difference. That large amounts of data can have very small information content. If you think about measuring the temperature in a room, and you're doing that once a second, that's over 3,500 data points in an hour. But if the temperature stayed the same, 70 degrees for that whole hour, how much information is that? That's just one piece of information. It was 70 degrees for the whole hour. So, other than kind of keep alive information from individual devices, from a storage perspective, if you want to do machine learning, or if you want to do further analytics or reporting, you don't need those 1,000 data points. You just need to know that between this time period, the temperature was 70 degrees. And so you can start to think about how do you convert the information content, the data content, to information. And that's really what we mean by only store the minimum. You're storing the information. And how do you also, at the same time, correlate events so that you can do immediate responses, so that you can react instantly, right? So if, with that temperature scenario, if the temperature suddenly, over a period of less than a minute, increased to 200 degrees, then there's a good chance the room's on fire. Right? So you can react immediately to that. As soon as you see that temperature starting to rise rapidly, you need to be able to react immediately to it. And there are obviously much more critical situations that you have to respond to even faster. You're measuring the speed of a turbine. If it suddenly drops, you need to be able to react in milliseconds. So those are the things we're talking about here. How do you work on the data so you only store the minimum, while at the same time being able to react immediately and give proactive responses when you actually need to? And doing this to, obviously, for operational efficiency, but then also to better serve customers, protect your reputation, and beat competitors. Because innovation is really what drives the competitive nature of our society. And if you can out-innovate people, or you can come up with new ways of doing things, you can disrupt and you can change things. And that's the way that competition works. And it's not just IoT data that is streaming. And the reason I mention this is because if you're getting device data as data streams, we already talked about that you need to be able to get the data in a streaming fashion because you can't store all of it. But if you're getting that data as data streams, then in order to make best use of it, in order to correlate it with other stuff and make instant decisions based on correlations between IoT data and what's going on in the enterprise and databases and what's going on in the machine that's written to logs, all of that needs to be streaming as well. And it's just a historical thing that we deal with all of that rest of that data in batches. Now, if you think about why we have batch processing of data, it's really because historically storage was cheaper than CPU and memory. And in fact, having enough memory to do like a daily batch job was just out of the question. But you could store that data and process it from disk and right back to disk. So the notion of batches is really an artifact of previous technology limitations. But if you have sufficient CPU and memory, and both CPU and memory are getting much, much cheaper, then you can start to think about, instead of doing queries against the database, do change data capture and turn that into a data stream. Instead of processing machine logs a log at a time, you read at the end of the log file and stream that out in real time. So that gives you the notion of all of your data in an enterprise, not just IoT data, being streaming, which then means that stream processing is a major infrastructure requirement. And by stream processing, I mean the in-memory processing and analytics of data before it ever hits disk in a structured way in order to create some business outcome. And this is part of overall data modernization. We're seeing that across a lot of our customers, and it's definitely evident across kind of the whole industry, that there's this notion that there's a lot of value in older data and older data stores, legacy data stores. And legacy can mean 3 years old these days. But there's a lot of value in that data. And you can't just rip out everything old and replace it with something new. For example, if you're a manufacturing plant, manufacturing equipment doesn't work on internet times. It's not like an iPhone where some people replace it every year. It's something that maybe has a 10, 20-year lifespan. And you can't just rip all of that out and replace it with something new because it sounds like a good idea or because it's trendy. It has to be done in a methodical way. And typically, as these things age out. So how do you access that data and work with that as part of your IoT assets and incorporate that with some of the newer data you have? So you can have an older manufacturing plant that has robots and things in it. And maybe that data is being written to a historian, which is a database. And now you can stream that data out by doing change data capture on that database. And then you have live data from that. And maybe you want to augment that by slapping on new sensors onto the motors on the robot that will measure vibration and temperature and movement and all of these things and correlate the old data with the new data in order to make sure the robot's behaving properly. So when you think about data modernization, it's not about replacing old castles with shiny new skyscrapers. It's about how do you incorporate the new technologies with the old technologies. And some of the things we hear from our customers are, the things that they have today, the legacy systems, they either can't keep up or they expect that in the future, the data volumes are going to massively increase. And they need to be able to be prepared for that and need to be able to deal with that. Or the latency in their applications is too high. Maybe they're writing everything to a database and they're doing batch processing on that afterwards, which is going to give them, maybe 2-3 hour timeframes before they know something. And they want to move to more, 5-10 second timeframes before they know something. And then in addition to that, there's a lot of pressure on the people within organizations that do analytics to produce new applications and to produce new ways of viewing things. And a lot of this comes down to our exposure as consumers to things like smartphones. We are used to now having information at our fingertips, being able to receive instant messages and instant video and instant news. Everything is just there. And the interfaces, the ways that we access these things is also very easy. We have very easy access to real-time information. And as consumers, we're used to that. When you move to an enterprise scenario and you want the same out of your business systems or your manufacturing systems or whatever, it's much harder to get to because things maybe weren't architected that way. And when you're asked to produce new outputs, new applications, new views, new reports on that, you need to be nimble as an analytics department, a data science department, to be able to keep up with all the demands that you're getting. So we need to think about architectures that can handle all of those things without necessarily ripping and replacing all of the existing systems. And if you think about manufacturing, for example, there was a very hierarchical view of kind of how manufacturing looked, all the way from the individual sensors and devices, going through kind of control levels and then manufacturing execution systems, all the way through to kind of ERP, which basically managed the supply chain. And that kind of hierarchical, very rigid architecture with specific things at different places, and processing done in particular areas, is being replaced with this more general architecture that has devices on one end and applications on the other end, with processing and analytics and storage happening wherever it makes sense. And this may be termed the fog. You may call some pieces on here first receivers. It's really what how you want to term it, but at the end of the day, it's an architecture that incorporates the processing, analytics, and storage and movement of data in a very flexible way that enables lots of different types of applications to be produced that can both minimize your amount of data that you need to store, so you can manage huge amounts of data, but can also react immediately. And that kind of smart data architecture can be very varied. And I'm going to give you some different flavors of ways of piecing together this architecture that can solve different scenarios, right? So you have to think about kind of the requirements here. We need to be able to collect and process data, perform analytics, be able to take actions on the data and on the results of analytics, things we find out, visualize results, and do this at the edge, in the cloud, on premise, wherever it makes sense for a particular application. Let's start with the simplest kind of IoT architecture. And this is what a lot of people kind of think about as IoT. And you have devices and they send data to the cloud. And that's where you do your processing and analytics. And yeah, there's a lot of examples of that, but there are also a lot of issues with that kind of architecture. For a start, not every device you're interested in is I. It doesn't speak I. It doesn't know internet, right? There's a lot of legacy devices out there that you want to be able to connect into this type of architecture, but how do you manage that? How do you turn them into kind of internet-enabled things? And the other thing is maybe you need to react fast. You're not going to be able to react fast if all of your processing is in the cloud. So two of the things we're trying to solve here aren't solved by this architecture. We can solve the things thing, and there's a lot of discussions and momentum around protocol translation gateways. Protocol translation gateway is like C-3PO from Star Wars. It knows how to talk to both modern robots like R2-D2 and also the dehumidifiers that were working in the desert to pull water out of the air. So you need to be able to talk to your manufacturing equipment, old school things that are wired into boxes that talk BACnet and Modbus and Zigbee and some of those other protocols, and integrate that with the new devices that talk MQTT or AMQP over TCP, right? So the protocol translation gateways, they work with that. Microsoft has one with IoT Edge. There's work going on within a consortium organized by Dell, the EdgeX Foundry, whose goal is to produce a modular protocol translation gateway. But it's not enough, though, just to do the protocol translation at the edge. Because if you're just doing that and you're sending everything up into the cloud, you're still missing out on things. You're not doing your analytics quickly and be able to respond rapidly. You don't have this flexible architecture, and you're sending huge amounts of data over a network into the cloud that you maybe don't even need to. So that's where you start to have to think about doing edge processing and analytics also within the gateway. And so you can start to do things like change detection. So instead of sending all the data into the cloud, you only send the data into the cloud when it changes with pings, heartbeats to let you know the device is still alive. So instead of sending the 3,500 data points a second from your thermostat or your 1,000 data points a second from your turbine, you just send it when it changes and a heartbeat to say that I'm still alive. Right? So you can do that kind of thing at the edge. And you can also do analytics. You can look for unusual patterns or anomalies and then alert on that and maybe respond and change and modify devices, stop things from happening, sound alarms, that kind of thing, and do that at the edge as well, so you can get this really fast response. And that type of thing often involves machine learning. So a model that you can use here is you take not the data, but the information content from the results of the processing and analytics, you move that into the cloud, you do that across a large number of areas, and now the cloud is accumulating information, not the raw data, but information, which can be used to perform machine learning. Now, once you perform the machine learning and you've built a model and you've tested that model and it looks like it's valid, you can then move that model to the edge. Once the model's at the edge, it can be used to make predictions in real time close to where the data is being generated. It can also be used for anomaly detection to look for unusual behavior and a whole bunch of other things that you can imagine machine learning could be used for. So this is kind of a general reference architecture of how you would incorporate machine learning into IoT. And obviously that can then be scaled up. You can add in multiple additional nodes within a particular site. You can add additional sites. You can accumulate all of that information in the cloud, perform the machine learning, export the models, and do your edge analytics. So now you've done a lot of the things we talked about. You've reduced the amount of data down because you're sending only information to the cloud. And you're also able to do processing and analytics at the edge, which enables you to respond rapidly to issues, send alerts, maybe send those alerts into the cloud as well, so you can have a visual view over everything that's happening across all of your sites. So this kind of architecture works really well for a lot of different use cases where you have information in a lot of different sites that you need to be able to view in a single place. But in a number of different scenarios, you can imagine that you want to also add in on-site processing and analytics. And this could be for a number of reasons. It could be because you need to be able to manage an individual facility or an individual production line and do that separately from a lot of other things. And it requires not just very specialized algorithms and specialized views into things, but you also need to be able to react more quickly than if the data had to make it all the way into the cloud. And you may want to repeat that across a number of sites. They all have their own autonomy. But then you also have situations like, imagine this isn't manufacturing, imagine it's healthcare. In a healthcare scenario, you may not be allowed to send a lot of this data into the cloud in the form that it is on premise. You may have patient data in there that is protected by HIPAA and other regulations, and that may not be permissible to send that into a cloud. But what you may be able to do is to anonymize that data. And so if within a hospital, you can view everything that's happening based on the architecture with kind of localized processing and analytics for an individual hospital. But data that's sent up into the cloud is anonymized, the identifying patient information is removed. Then you can additionally do machine learning in the cloud You can also view across a whole bunch of different hospitals, status of things and where you are with things like inventory and other stuff. But what you can do with a machine learning is maybe you can look at trends and look for correlations between information about patients in an anonymized fashion, maybe looking for combinations of different measurements on that patient and what their symptoms are, and look for relationships between those that you may not have spotted before, and then apply that machine learning close to the patient. So you can start to think of a healthcare scenario using anonymized data being produced by huge amounts of hospitals that will help you save patients' lives, because you can now look for things and learn things about patients that you wouldn't have been able to do before. So if you have an architecture like this, it's enabling you to connect anything, because you have the internet-enabled IoT, which you can already talk to. You already do MQTT, AMQP, TCP, HTTP, whatever protocol it's using. But you also have the protocol translation gateway that has modules that allow you to speak to BACnet and Modbus and OPC UA and all these other things that talk to more and more devices. It allows you to react immediately because you're doing the edge processing and analytics, and also limit the data sent to the cloud and change that data to information before it ever makes it into the cloud to make everything much more efficient. It obviously will scale as required, because you are moving a lot of the processing to kind of edge devices, and edge devices can inherently scale just by adding more of them and add more on-site processing and analytics as necessary, and scale out the cloud, because that's what the cloud is designed to do. With the ability to control everything centrally through a cloud interface. So not just be able to visualize everything, but be able to work with everything centrally through a cloud interface. Now, IoT, as I mentioned, is not a separate thing. So to get the full picture, you have to join together not just the IoT data, but you have to also bring in other enterprise data. So you start looking at things like finance information, customer information, supply chain, inventory, all of those things. And the biggest value that you're going to get from IoT is when you can join that data with your IoT data. So for example would be, if you have a sensor on a motor, and that sensor is just sending out data, say over MQTT, and the data it's sending is device ID XYZ value 3. That doesn't mean much from an analytics perspective. You know it's a sensor, you know it's sending out value 3, you're not quite sure what that means or what that sensor is, where it is. But if you can join that sensor information with information that you have in your asset database, with information you have in your ERP system, then you'll find that this is a sensor and it's measuring vibration levels on a motor that was bought 3 years ago with a warranty of 3 years and with an average lifespan that you've seen in your dealings with this type of motor of 3.2 years. And that's going to start to give you much more information for your analytics. Now, that information wasn't present in the IoT side of the world, but it's present in the other enterprise assets that you have. That's just a very simple example, but I'm sure you can think of hundreds of more examples where by augmenting IoT data with other data, it just makes it so much more valuable. I mentioned machine learning. The way that you really integrate machine learning is that you need to be able to work with data, first of all. So a lot of the machine learning algorithms, they're kind of sensitive and picky to the format of the data that you give it to train it. They tend to work best when you present all variables together in a single row. and so that you can train the model based on the correlations and relationships between variables. There are algorithms that work with time series data and receiving events over time that are more complex. But a key thing within machine learning is you need to process and prepare data and get it ready for the learning first. And what you want to try and do is make sure the same data that you're using to prepare machine learning and train a model can in future be used to perform real-time scoring, inference, predictions, anomaly detection, classification, or whatever it is you're doing, can be done on the same data. Right? So if you take a look at this flow, you take the data wherever it's coming from, IoT and maybe some enterprise data, join that together, prepare it, get it into the right format, write that out to files, and then have data scientists run their magic against the files and build a machine learning model. And obviously test that, validate it against the data, ensure that it's correct, export that model, and then utilize that within a streaming architecture. So now the same data that is being accumulated for training can be passed into the in-memory streaming part and compared against the model, push through the model and see what the model tells you about it. And so that would enable you then to immediately, on real-time data, see if an anomaly was occurring, or on real-time data, predict when something was going to fail, or classify something in some way based on the data you're getting. Maybe it's image classification. Right? So all these things can be done if you have this kind of architecture that enables you to train the machine learning model and to do real-time scoring. And of course, if you're seeing that the model isn't working well, because you're continually accumulating training files, you can then also retrain the model and re-export it and resend it back into the streaming side and now work with a new updated model. So that it makes that whole process much easier. The other thing that I mentioned, and this is something that we see customers doing, is if you have on-premise manufacturing equipment or other equipment that is not IoT, it's just T, they're things, but they're not already hooked up into the internet. Maybe they're writing their data into a historian database. Then by utilizing change data capture and doing that within the framework of this architecture that I've just talked about, you can treat historian data as if it was real-time IoT data being sent to you in any other way. So it's a way of modernizing your existing investments in manufacturing or in other equipment that writes to a database, medical information that writes to a database, for example. By using change data capture and streaming out what's being written to the database in real time, you now have a stream of your IoT data as well. So just talk about some use cases of these architectures. One obvious one is actually cybersecurity. Now, a lot of new approaches to kind of cybersecurity do incorporate machine learning. So it's about looking at what is normal behavior and classifying that as normal behavior, and then being able to spot unusual behavior really quickly. And the best way of doing that is by collecting and correlating as much data as you can. It's easier to fake a single piece of data than it is to fake a whole collection of data from a lot of different sources. If you think about Stuxnet, Stuxnet was a virus that infected the control systems of centrifuges that were making nuclear material. And it did two things through centrifuges in a simplistic fashion. It made them spin faster so they would destroy themselves, and it also told the people monitoring the centrifuges that everything was okay, to give them time to destroy themselves. Now, if you are also measuring a whole bunch of other information about those things, like vibration levels and power draw, maybe video imagery of those things, and correlating that with what you were being told, you will see that what you're being told isn't actually what's happening. And so by utilizing machine learning and incorporating IoT data with other data that you may have, maybe network data, seeing if there's been a security breach, all these things, you get to get a much bigger picture of the security around IoT. And this also works for kind of enterprise security as well. But in the context of IoT security, it's essential to correlate as much information as possible. Another example where machine learning can be very important is in production quality, where you collect and analyze device data and you predict out with machine learning what you expect the quality of the end result to be based on what you've seen in the past. And so instead of a widget making it all the way down a production line only to go in the reject box, you may spot very early on that based on what we've learned in our machine learning models, if the parameters of the widget are outside a certain range at this point in the production line, then it's going to fail anyway. So by incorporating machine learning and sensor data and the architecture that I mentioned with edge analytics based on machine learning, you can start to get a better picture of production quality, and that actually ends up with a massive ROI because you're not wasting anywhere near as much raw materials or pieces as you're building and moving down the production line. Similar story with healthcare monitoring. Now, it's one thing to be able to measure certain aspects and parameters of a patient, but if you can join all of that with multiple medical devices, patient data, potentially utilizing machine learning on anonymized data to enable you to look for anomalies or potential issues. Like if, for example, if you had additional information about a diabetes patient, in addition to glucose measurements, you knew when they last ate, whether they'd been out for a walk recently, what their heart rate was, and you could combine it and correlate all this together, compare that against the model, you would be able to track immediately if this patient was at risk. So again, by joining together lots of different patient information, running it through models, you can have immediate insights into patients and react immediately. And also, if you can somehow get everyone to collaborate, you can get large-scale data, again, anonymized, to look for trends, so spot outbreaks and things like that very quickly. And a final example, again, using the similar architecture, is location tracking. And location is a really important aspect of IoT and is also a really important aspect of any, or reason why you need stream processing. The thing about location is things move around a lot and they move around quickly, and you want to be able to deal with them quickly. And we had an example where with a partner building a airport monitoring system, and that involved monitoring the locations of thousands of passengers in real time and staff in real time, identifying multiple different zones and looking for when people walked in and out of zones and how long they were waiting there for. And the purpose of this was if too many people were waiting in one particular area, maybe it was in ticketing, then you could automate sending more staff to that area to deal with them. And also if people walked out into an area they weren't supposed to go to, into a secure area, then you could spot that immediately and send someone there as well. But location tracking is generally a useful thing. A lot of people are used to real-time with locations. If you're driving, you're probably used to using Waze, which gives you real-time insights into accidents around you and real-time routing. Real-time is essential, and streaming is essential when it comes to location monitoring of any kind. But it has benefits in manufacturing, healthcare, retail, aviation, etc. If you think about one question I like to ask people is, what have airports and hospitals got in common? And the answer is problems with wheelchairs. Not knowing where essential equipment like a wheelchair is all the time can delay planes and can delay patient treatment in hospitals. So being able to monitor these things in real time is also essential. Location tracking, I think we're going to see a lot more of this type of application as real-time analytics and processing really start to pick up steam. So just a little bit about us before I finish off the presentation and open it up for questions. The Stream platform is a complete end-to-end platform that supports streaming integration analytics across enterprise cloud and IoT. We have a flexible architecture that allows you to deploy data flows across on-premise and the cloud and processing at the edge. We do continuous data collection from not just IoT devices and sensors and message queues, but also from files by reading at the end and from databases through change data capture. And then we allow you to do the stream processing in memory with real-time filtering, transformation, aggregation, enrichment, and do all of this through a SQL-based language. It makes it easy for anyone to work with. You can also do streaming analytics, so correlation of multiple data streams, complex event processing, statistical analysis, integration of machine learning models, and then also build visualizations and alerts and kind of trigger external systems, and deliver the results of the collection, the processing, the analytics to anywhere, to databases, files, big data, Kafka, cloud, etc. We integrate with a lot of existing enterprise software, open source as well as proprietary things like databases. And we do all of this in an enterprise-grade fashion that is inherently clustered, distributed, scalable, reliable, and secure. Now, we are a streaming integration analytics platform that supports IoT. And we support specifically the integration of IoT data with all the rest of the data that you need to give value to that IoT data. When you're building applications through our platform, you do so with data flows. You start with sources, you do processing through SQL, and you end up triggering something, writing data somewhere. And you can also build dashboards, live streaming visualizations by dragging and dropping visualizations that give you a view into whatever the back-end processing is you're doing. So you can see how you can build up IoT applications really easily. They're starting off with IoT data sources, MQTT, AMQP, whatever you have already. We have examples actually working with Arduino devices and working with model factories and things like that. They're kind of easy to get your hands around. And delivering that data to MQTT, processing that data, and then building a whole dashboard and visualization around it, as well as controlling the devices. We integrate with a whole bunch of stuff. This is an eye chart. You're welcome to come and look at this in the download of the presentation on the video. And we really differentiate ourselves by being an end-to-end platform, so everything that you need to actually start getting value out of your data immediately, but easy to use, so you can build applications really quickly using our platform, and it's easy to deploy them as well without any coding necessary. It is an enterprise-grade platform, so it's inherently distributed, scalable, secure, reliable, and we have focused on a lot of the integration aspects, so we work with most of the data sources that you'll have. If you want to know more about us, here's all the links that you need. And with that, I'll open it up to any questions. I don't see any in the chat window right now, but if you don't have any questions, I can always ask myself some. We'll just wait for a short while, see if anyone comes up with anything. And let me just go back to the webcam. There we go. And let's just wait and see if anyone's going to ask any questions. So while people are thinking of really intelligent questions to ask me, I'll ask myself a question. So, aren't there lots of IoT platforms out there already? Kind of open source IoT platforms, proprietary IoT platforms that can get to the data? Well, yes, there are. And I think, as I mentioned in the presentation, and I've tried to say time and time again, a lot of the existing IoT platforms focus on IoT data and focus on just being able to access, collect, maybe just deliver that IoT data to the cloud, or if you're lucky, being able to do some processing and analytics on that IoT data. Now, if you want to get value out of that IoT data, typically you're going to need to join that with other data as well. And a lot of that other data is locked up in other places within the enterprise, and you need specific ways of getting to it, whether it's reading from files, whether it's parsing logs, whether it's accessing network information, or getting data from databases in real time. You need specific tools to be able to do that. And so what we've done in our platform is to look at IoT as another source of data. And yes, be able to do things like edge processing, but edge processing is also useful for security data, not just IoT data. That whole architecture is useful for a lot of different scenarios, not necessarily just with IoT data, but in any situation where you have huge volumes of data coming through. So I think I've exhausted myself with questions. Well, I could ask myself a lot more, but I'm not going to do that. I will give you guys a break and a little bit more time back. I think probably have 15 minutes left, so you get 15 minutes more of your day. And unless anyone has any last minute things they want to ask me, 5, 4, 3, 2, 1, I will end it there. Thank you.